All right, so for these notes, we're going to go over transformations and characteristics of exponential functions. So for exponential functions, we have the base of the exponent b, and then we have the exponent, which is where the variable comes in. So we have three important pieces of information. Here, instead of having a vertex, this is kind of going to feel like rational functions where we have an asymptote. So here we have the asymptote is a horizontal asymptote. We do not have a vertical asymptote. And for the parent graph, the asymptote is y equals 0. And then we have two other important points we're always going to graph. We're always going to plug in 0. And if you plug 0 into this function, if you plug 0 in for x, you get b to the 0. And anything to the 0 power is 1. So we get the point 0, 1. And then we're always going to plug in 1. So if you plug in 1, you get b to the first power, which is just b. So for this particular graph, we have whatever the base happens to be, 1, and then if the base is 2, it'd be 1, 2. If the base was 3, it'd be 1, 3. If the base was 4, it'd be 1, 4. So what we're going to do for this parent graph is we're going to do y equals 2 to the x. And so this is going to have a horizontal asymptote at 0. It's going to have the point 0, 1. It's going to have the point 1, 2. And then we know about asymptotes, we know that the behavior of those is that as the graph gets closer, as the curve gets closer to the asymptote, that the distance between the curve and the asymptote would approach 0. We know that's the definition of an asymptote. So over here, the graph is going to approach the asymptote, and then the way an exponential graph grows is that it grows exponentially. And so it gets really big really fast. So this is what our exponential graph is going to look like. I'm going to leave this other parent graph to go over tomorrow in class. This is e to the x. We'll talk about that one tomorrow in class. So these transformations are going to be like what we expect for all the other parent graphs that we see. So we're going to call B the growth rate. So it's not really a transformation, but we're always going to find it because we want to make sure that we don't get our growth rate confused with our vertical stretch or vertical compression. And then we're just going to remember that a negative A is a reflect over x, and that the absolute value of a being greater than 1 is a vertical stretch. Absolute value of a being less than 1 is a vertical compression. And that h, if it's positive, it's moving the graph to the left. If it's negative, it moves the graph to the right. K, if it's positive, it moves the graph up. If it's negative, it moves the graph down. So all the transformations are the same as what we recall for all of the different parent graphs that we have studied so far. So here the only difference is from the other graphs is that kind of like rational functions, we don't have a vertex, we don't have a locator point. So like I said down here, exponential functions don't have a vertex or a locator point. They do have a vertical asymptote, or sorry, a horizontal asymptote, and the horizontal asymptote is y equals k. It would be good for you to circle that. So kind of similar to the rational functions in that they do have a horizontal asymptote, but kind of different because they don't have a vertical. So here, if we look at the transformations, if we wanted to graph this one, we would look and we would see that that growth factor is a 2. So we would start off this one with that information. We would say our horizontal asymptote is y equals 0. We would say we have the point 0, 1, and we would say that we have the point 1, 2. And then if we were to go through and do all the different transformations on this graph, on these important pieces of information, we would have a reflect over x. we would have a right 3, and we would have an up 1. And if we were to do that to each of our points for the horizontal asymptote, reflect over x, if there had been a number there, that would have become negative because it is a y value, but it doesn't, -0 doesn't do anything. So I would keep, I'm going to go ahead and make my chart here. So I'm going to keep my horizontal asymptote at y equals 0. I'm going to have 0, -1, 1, -2. There's my reflect over x. And then I can go ahead and shift my graph to the right 3, and then I can go ahead and shift my graph up 1 and up 1, so there's my 2 points, and then the horizontal asymptote, when I shift it up 1, we know that that's going to shift up 1 as well. And so you can see the horizontal asymptote in the equation, it's the number on the end. So, and that's exactly the same as what we learned in our last unit on rational functions. The number on the end was the horizontal asymptote, so that's going to feel somewhat familiar. So horizontal asymptote, y equals 1. So you can see that y equals +1 there. There's that horizontal asymptote, and then we have the point 3, 0 right here. We have the point 4, -1 right there. So if we needed to graph one of those functions by hand, that's how we would do it, is we would take that important information and we would take those 2 points, the 0, 1, the 1 base. The base here happens to be 2. So that 2 was not a reflection, or was not a compression, was not a vertical stretch. It was actually the growth factor for the problem. It was the base. It was the base of the problem. All right. Next, let's go ahead and do domain and range. So we'll move on to the next example. This one has a base of e. That's okay. We can still do the problem. So here I'm going to go ahead and label what my horizontal asymptote is. We do remember from rational functions, hopefully, that the horizontal asymptote does have to do with the range, so it's good to find that before you find your range. But if we look at the domain for this problem, I can see that the graph does go left forever, it does go right forever. So my exponential equations are always going to have a domain from -infinity to +infinity. But because they do have horizontal asymptotes, that range is going to be limited. So typically, if they have nothing that is, if they're right side up, so they're going up, then it's going to be something limiting them from the bottom. So here, this graph goes from -4 to infinity. It's a parenthesis because we have an asymptote. It's not going to be a bracket. If this graph had been reflected upside down, like this last one, this one would have had a range of -infinity up to 1. So the domain is always going to be all real numbers, -infinity to infinity, but that range is going to be limited. All right, let's go ahead and do the increasing and decreasing intervals as well. So for the increasing and decreasing intervals on this one, we just have to label our x values. So we know that increasing and decreasing are always x values. Left arrow is a -infinity, right arrow is a +infinity. And then if we look here and we have our little stick figure guy, it looks like he's walking kind of like up over a hill. And the hill does look like it levels off, but we know that it's approaching that asymptote, that horizontal asymptote of -2. He's going to get closer and closer and closer to it. So this is going to be kind of like when you're walking or riding a bike, and as you look ahead, it feels like you're walking on flat ground, or it looks like you're walking on flat ground, but you can feel that you're inclining because you're working a little bit hard. You can feel it in your muscles, but you can't really see it. Is what's happening here. So we know it's not flat because there is a slight increase, even though to our eye it kind of looks like it should be flat. So this is an increase all the way, which means that for decrease we're going to put none, and for increase we're going to say -infinity to +infinity. So even though it looks flat, we know there is a little bit of an increase there. And if we were walking it ourselves, we'd be able to feel a little bit of a muscle burn on that one. All right, x-intercepts and y-intercepts. I want to make sure that we're going to do this one together in class because I do want to make sure everyone can find that E button on their calculator, and I'll be showing that to to you guys tomorrow as we do that other graphing problem on the front page, so do not worry about doing this one on your own. The end behavior is going to feel very similar to what you guys did with those rational functions. So here, we're going to say as x goes to the left, so as we look at that left arrow, as we look at that right arrow, this is going to feel very similar to rational, but slightly different. So for this one, as we look at the left arrow, we can see that the left arrow would be approaching that horizontal asymptote. So for this one, the left arrow is approaching the horizontal asymptote, which we know is the k value. But the right arrow on this one is going up. So for this particular example, the left arrow would be going to the horizontal asymptote, which is k value. The right arrow would be going to positive infinity. For this one, we look at our left arrow and look at our right arrow. The left arrow would still be going to that horizontal asymptote. And then the right arrow would be going to negative infinity. So that gives you a little bit of a clue about how these are going to work out when you look at the end behavior. Again, do not worry about graphing the last two. We're going to be doing those in class.